Hey there, folks. I am going to take you through Redox Part 2, or basically how to make a battery. And we're going to use Table J to help us with that. This video will mostly be about Table J. The next video will be about how to make a battery, how to analyze a battery or a voltaic cell. Here we go. Okay, you may have learned this in elementary school. Electricity is the flow or movement of electrons. When you have moving electrons, you have electricity. Okay? Now, if you've got a flow of electrons, that means electrons are leaving one place and arriving at a different place. Okay, electrons are flowing from one end of this battery and then going to the light bulb to light it up, and then their electrons are going back to the other side of the battery. Hey, so if you've got electrons moving, you've got one thing losing electrons and one thing gaining electrons. That's redox. That's oxidation reduction. That's what this unit is about. So to make a battery, you need redox. Okay, so the battery that's in your flashlight, or that's in your smoke detector, or that's in your grandpa's hearing aid, or that's in your old cell phone, or that's in your iPhone, those all basically have two elements in them, usually two different metals, okay? And one of those metals gets oxidized, and one of those metals gets reduced. Oxidation and reduction always go together. And when you have that, you have electrons moving from one place to another, you're generating electricity. Okay. Now, I'm going to do a demo for you really quickly with a piece of copper and a piece of zinc and a lemon, which is a nice source of acid, which is a way to get this reaction going. And then I've got a multimeter. That's a little gadget that measures voltage or current or resistance. It basically measures electricity. It tells you if electricity is flowing. Okay. All right. So here's the demo. Okay, I've got a multimeter with these two probes. I've got a lemon with a piece of zinc and a piece of copper stuck in it. A multimeter will detect electric current, among other things. So I'm going to touch the probes to the zinc and to the copper and watch the needle on the multimeter. 1, 2, 3. Look at that needle. We are generating electric current. We have made a battery. One metal is being reduced, one metal is being oxidized. We are making electrons flow. One thing is losing electrons, one thing is gaining electrons. That's making electrons flow through the wire. And the multimeter is detecting that flow of electrons. It's electricity. It's a battery. Okay, in that demo, we saw that we had zinc and copper, and if I didn't have a complete circuit, no electricity was flowing. But you knew from elementary school that, okay, electricity can only flow when you have a complete circuit. When we complete the circuit and the probe is touching the zinc and touching the copper, we've got electricity flowing. The needle is all the way to the right. Now, when if you have worked ahead in the HyperDoc, you may have seen diagrams that look like this, and they tell you, oh, this is a voltaic cell. Well, that's what a battery is. A battery is a neat package that basically contains a solution with some ions and one metal, and a solution with some ions and another metal, and they're connected through this thing called a salt bridge. And a voltmeter is just a way to measure the electrical current. And we can see, oh, electrons are moving through the wire. The salt bridge is a way so that ions can get back and forth between the two containers. And a battery like this Duracell is just a cleverly packaged version of this voltaic cell. Okay, one thing to remember about metals, how to be totally metal. What do metals like to do? Now, you may or may not remember, francium is the most metallic element on the periodic table. Francium really, really, really loves to lose electrons to get a stable octet. That's what all metals want to do. Metals love to undergo oxidation. Remember, Leo says Gur, loss of electrons is oxidation. Metals love to lose those 1 or 2 valence electrons that they've got. They love to form positive ions or cations. So metals will always lose electrons to form positive cations. Okay, that brings us to Table J. Table J is called the activity series. Basically, it should be called the reactivity series. It's a ranking of which metals are most active or most reactive. The ones at the top are the most active. Now for metals, that means the ones that are most likely to oxidize. So basically, the metals that are at the top are more likely to oxidize than the metals at the bottom. And this is going to become important later. If you have two metals, and one is a solid and one is an ion in solution, if your solid metal is higher than your ion that's your metal, if your solid metal is higher than your metal ion, a spontaneous reaction will occur. If your solid metal is higher up on this list than your ion metal, a reaction will occur. Okay. Now, one weird thing about table J, hydrogen is on there. Hydrogen is not a metal, no, but hydrogen loves to form H+ ions just like other metals do, Na+, K+, etc. Okay, so hydrogen can be oxidized. It's on this list. Just don't be freaked out by that. Okay. All right. Now I've got another demo for you. Okay. Now this demo is too small to see in video form, so I'm just going to show you some screen close-ups. Okay. I've got a close-up of a test tube. I'm going to put a piece of a zinc, solid zinc, into this test tube containing copper ions, a copper sulfate solution. So it's got copper ions. So my zinc is a solid metal. My copper is a metal in its ionic form. Watch what happens as time goes on, okay? As time goes on, look closely at the zinc solid. Time is passing, time is passing, time is passing. Look at that solid zinc. The solid zinc is coated with fuzz. What is that fuzz? It's actually copper crystals. The copper ions are turning into copper atoms and on the surface of that piece of zinc. Now, we started with a nice shiny piece of zinc, and after a while, that zinc became coated with fuzzy copper crystals. Before, after. This reaction happened spontaneously. It just happened. We didn't need to add any energy to force it to happen. Now, one interesting thing is that if we take solid zinc and we put it in copper ions, we get a spontaneous reaction. Okay, the copper ions turn into copper solid. But if you do the opposite, if you take a solid piece of copper and put it in a test tube full of zinc ions, nothing is going to happen. And the way you can predict which of these will be a spontaneous reaction and which one will have nothing happen is with table J. Okay, so let's analyze this a little bit. Okay, table J, zinc, copper. Which of these is higher up on table J, zinc or copper? Hit pause, look in table J and see, is zinc higher or is copper higher? Okay. Hopefully you found that zinc is higher. Now, in this case, we've got solid zinc, okay? I've got a little lump of zinc that I'm going to put in this beaker full of copper ions. So zinc is our solid, our free element, and copper is our ion metal in this case. And if the solid is higher than the ion, a spontaneous reaction should occur. Well, what we saw when that zinc went into the copper solution, yeah, we had a reaction that did occur spontaneously. Copper fuzz formed on that piece of zinc. Where'd the copper come from? It came from the ions in solution. Okay, so the zinc got oxidized because it's higher on table J. Things that are high on table J get oxidized. Things that are lower down on table J are more likely to be reduced. Okay, so when zinc gets oxidized, Leo says Gur tells us a loss of electrons is oxidation. Solid zinc turns into zinc ions and it loses electrons. That's oxidation. The copper gains electrons. Gain of electrons is reduction. The copper ions gain some electrons and they turn into copper solid. So that fuzz used to be copper ions. It turned into copper solid. And the zinc that was solid, it turns into copper ions. And when this happens, the zinc loses 2 electrons and the copper gains 2 electrons. Where do the electrons come from for the copper? They come from the zinc that's losing the electrons. You can't have oxidation without having reduction. Okay? So table J tells you which metal will oxidize. Table J tells you that if the solid metal is higher than the metal ion, a reaction will occur. Okay? We saw that solid zinc with copper ions did have a spontaneous reaction. But if we try copper solid with zinc ions, well, copper is not above zinc. So we don't get a spontaneous reaction. But we will get a spontaneous reaction with magnesium solid and Fe ions. Why? Because magnesium is up here and iron is down here. If the solid is above the ion, then we will get a spontaneous reaction. Another example of one that won't be spontaneous, though, nickel solid with aluminum ions. Okay, where is nickel? Nickel, nickel, nickel. Okay, if we have nickel solid with aluminum ions, okay, well, it'll only be spontaneous if the solid is above the ion. But in this case, we've got solid nickel below the aluminum ion, so it won't be spontaneous.